third NPTEL session, and that is recorded session. So the content I will be going to cover in this session is first I will be going to discuss the derivation of thermal time scale. Then I will be going to discuss numerical on that. Then after that I will be going to discuss the difference between two frame of reference, that is Eulerian and Lagrangian. Then I will be discussing the relation between Eulerian and Lagrangian derivative. I thought these are the four things in which you will be going to have a doubt, and so I choose to record the session on these four uh, points. Okay, so before starting this session, I want to clarify one doubt that was raised in the last session, that is that what happened when in the Stokes flow. So when we are so I showed one example where there is a cylinder where there is a fluid flow, where there is a fluid and there are dye particle, and I rotated that in one direction, and then I showed that it is rotated when it is rotated in one direction. It's a viscous fluid with viscous fluid. So it's a viscous fluid with some sort of a dye particle, and so when you rotate, it gets diffused, and when you rotate back, they come back to the same position. So the question was asked that where this energy is going, this rotational energy is going. So this rotational energy is basically going to uh, going in the viscous dissipation, which leads to the increase in the diffusion, and this diffusion leads that there is some kind of diffusion. So what is the important, and that was asked that when we rotate it back, then there is again. So I wanted to clarify that when you rotate in any of the direction, there is a diffusion, there is a molecular diffusion, and that molecular diffusion is not dominating. So molecular diffusion is not that dominating, due to which you will see flow reversibility. That the energy of rotation is going into the diffusion, but that energy is comparatively so we are very slowly rotating that, and that energy is very uh, is very it's not that significant that you will able to see the diffusion, though there is a diffusion due to this energy, due to this extra energy, but you will not able to see the diffusion. And most of the dominance is by the fluid flow, that is the pressure gradient, and the pressure gradient applied in one direction, which leads to the flow of streamlines in one direction. And then when you reverse the gradient or pressure gradient, then you will see it comes back. So that is the point I would like to clarify. Okay, I hope it is clear now. If you have any doubt, you can always mail me at this email address. So that is all for the last lecture, the doubt regarding the last lecture or the last session. So now let's derive the derivation of uh, thermal time scale. Okay, so thermal time scale. So basically thermal time scale, we have already discussed particle or the disperse phase time scale, that is the particle time scale, and that we have shown that it is the how the it is the time in which the particle responds to the fluid velocity, or the or how it is affected by the fluid. Now in thermal time scale, it is also similarly defined to that of uh, particle time scale, and the definition is like this. So thermal time scale of a particle similarly defines how or I can remove thermal time scale of particle defines how fast it thermally respond to a change in temperature of the surrounding continuous phase. Okay, so let's say so in order to find this thermal time scale, let us consider a particle having initial temperature Tp naught, which is surrounded by an ambient fluid flow of Reynolds number Re. Okay, the temperature the temperature of the fluid or the continuous phase is fixed, that is Tc. Fixed means to say that when there is a particle, so whatever the heat transfer is there in between the continuous phase and the particle, there shouldn't be any change in the temperature of the continuous phase. It's like a heat bath, uh, or we can say that whatever the temperature it is at, it will remain as it is. Okay. So we need to find out the time scale on which the changes occurs, and that is called the thermal time scale of the particle. So if particle has having temperature Tp naught at T is equals to 0, temperature is Tp naught, and let's say some instantaneous temperature is Tp and surrounding temperature is fluid temperature is Tc. So this is particle and surrounding ambient temperature is Tc. So there is a heat transfer, and the equation of thermal evolution of the particle can be written as so that is basically the balance of rate of change of energy stored within the particle should be equal to the heat loss due to conduction or convection. Okay, so that is, so rate of change of energy stored within the particle is rho p Vp Cp dTp by dt. Tp is the instantaneous particle temperature, and that should be equal to 2 pi kf dp Tc minus Tp and phi t. Kf here denotes the thermal conductivity, or instead of Kf I can write it's fluid, or you can say C, continuous phase. Thermal conductivity of continuous phase. Here phi t is actually the correction factor. Correction factor for finite Reynolds number. Okay, so basically we are as of now we are considering a finite Reynolds number, we are not considering a zero Reynolds number. So phi t can be explained based on the correlation, that is nu is equals to twice of phi t. Nu is nothing but the Nusselt number, that correlates the, and Nusselt number is the ratio of convective to conductive heat transfer. Okay, so basically this is defined as 2 plus 0.4 Re to the power 1 by 2 plus 0.06 Re to the power 2 by 3, and that is Pr to the power 0.4, 2 plus 0.6. So that is the correlation, that is the empirical correlation based on some experiments. Pr to the power 1 by 3. Here Pr is Prandtl number, which is defined as momentum diffusivity divided by thermal diffusivity. And thermal diffusivity we know that is Kf into kappa f into rho f into Cpf should be equals to thermal conductivity. So basically this is Prandtl number, and you can see that for zero, for Stokes flow, Nu basically Re is equals to 0, and so phi t should be 1, and also Nusselt number for the case of a sphere is 2. So Nusselt number for the case of a sphere we know is 2 in a uniform flow. For 0 Re. Okay. Basically we are assuming that whatever the loss that is attributed to the thermal conduction. Okay, that is conduction term. So now we need to find the thermal time scale. Okay, that we can call it to be thermal, that is called thermal time scale. So if we look at this equation, let's call it equation 1. So we know that dTp by dt should be phi t1, and so that is Tc minus Tp divided by tau t, that is the thermal time scale, and tau t can be obtained by putting the value of P, and so that comes out to be dP square rho C P by CPF divided by 12 kappa F into phi of T. That's the generalized expression, but for our case phi T you can take 1, and so tau T can be accordingly changed. Okay, so that is the thermal time scale. So I think I didn't describe Cp is the specific heat of the particle, and Cpf is the specific heat of the fluid or continuous phase. Both are at constant pressure. Okay, now we know what tau t is, so that is the main thing. Now we can solve this equation. So dTp by dt, and so what we get is ln tau p minus tau p should be equals to e to the power minus t by tau plus c, and we know that at t is equals to 0 Tp equals to Tp naught. So at t equals to 0, C is equals to ln of Tc minus Tp naught, and so what we get is ln Tc minus Tp divided by Tc minus Tp naught. Sorry, it shouldn't be E, it should be T by tau. So it will be T by tau, and so what we get is Tc minus Tp is equals to e to the power minus T by tau into Tc minus Tp naught. So Tp comes out to be Tc plus Tp naught minus Tc e to the power minus T by tau. So that is the temperature of the particle changing with time, and that is the thermal time scale. Okay, so I hope everything is clear. Now let's discuss one question on this. So the question is, initially a stationary particle is present in an ambient Stokes flow which is at temperature of 400 Kelvin, the temperature of the fluid is 300 Kelvin. Calculate the final temperature of particle at T is equals to 100 tau p. Okay, so let's solve this question. So basically the question is, we have to find the temperature at time t is to be equals to 100 tau p. So Tp is equals to Tc, we know that is 400 plus initial temperature of the fluid is the temperature of the continuous phase is 300 Kelvin. So that is so first write it like this. So Tc is 300 Kelvin. T of particle at T is equals to 0 is 400 Kelvin. So Tp is 300 plus 100 into e to the power minus 100. Okay, so let's solve this. So that is coming out to be 300 plus 3.72 into 10 to the power minus 44, and if you see this is very large, so it means that tau p equals to 300 Kelvin, and it means that it is almost reached to the ambient. So tau p is almost reached to the ambient fluid temperature. Okay, so that is this question. Now so first two parts are already discussed. Now let's discuss the difference between the two frame of reference, that is Eulerian and Lagrangian frame of reference. So what is Eulerian frame of reference and what is Lagrangian frame of reference? We need to discuss it. So frame of reference basically is the way of measuring different properties, different fluid flow properties. So basically we are having two frame of references, that are Eulerian and Lagrangian. Okay, so Eulerian is we called to be as fixed frame of reference, So it means that if some flow is flowing, so you sit here, you sit here, and you are looking at the fluid, and now you are thinking that so you fixed yourself here, you are not moving, and you are looking at the fluid, and let you are looking like what is happening to the fluid velocity. So basically you are calculating what is the change, whatever the velocity is changing between this and this. So basically you put your face at a particular position, and that is fixed, and then you are looking at the fluid. But in case of Lagrangian frame of reference, uh, you move along the fluid, move along the continuum, or we can call it as continuum point. So in this case there is a fluid flow, and what you are doing is, so let's say what we called as continuum point are the these if you put tracer and that is following this fluid flow, so these are the continuum point, or what we can say that these are the particle. So these are the fluid particle. So in all of these are present, and basically you are traveling with these points. So initially you are here, then you are here, then you are here. So as the fluid is flowing in this direction, you are also moving in this direction. But in this case fluid is moving in this direction, but you kept yourself at constant. So basically these are the two frame of references, two way to see the fluid, and both are their own benefits, and uh, you can use whatever you want to use according to the problem that you are solving. So basically what is the difference between these two is, as told earlier, in this case fluid motion is described by specifying properties of fluid as a function of space and time. Okay, while in this case you describe fluid properties fluid properties as a function of initial position of fluid particle. So in this case if you want to find the temperature, then it is dependent upon x naught and time, or I can x naught and time. But in this case if you want to find the temperature, you will fix it and find it at a particular position. Okay, so that is the main difference. So let's say at a particular point the velocity of the fluid particle is v, and that point is x. Okay, now uh, I think I can call this to be some zeta, that is the initial position of the fluid particle. So at this point the velocity of this particle is v. Okay, and so if this particle is following this path, so for just before reaching here, it is at some point, that is zeta. Now let's say you are, instead of here, you are at this position, zeta some delta zeta. Okay, and then this particle is following this. So this you are tracking this fluid particle, and then you are reaching here, and the velocity of this particle is fixed. Okay, so the main point to state here is that x is a function of initial position, initial particle position, and time. So that is what is the initial position, that is x is a function of it, of that. And velocity, the important statement is that velocity at a point x is the velocity of the fluid of the material point occupying x at that time. So basically we are so the velocity, if we are saying velocity is at x is fixed, this is v, so that is the velocity of all the particles that are coming from whatever the position it is coming, it is fixed because it is at a particular point. Okay, so that is the way this is the fixed frame of reference, and that is the way you can see this as Eulerian frame of reference, and you are tracking the particle from here to here or here to here, that is Lagrangian frame of reference. Okay, so basically let's find out the relation between the Eulerian and the material coordinate. So let's say we are having some material B that is there in Eulerian frame of reference, and it is passing through a point that is the, so that is the material, so sorry, that is the material frame of reference, that is material coordinate. And you are following some path and you are reaching a particular point x, and that x is a function of zeta and time. Okay, so that is Eulerian coordinate. So basically you are tracking from here to here, so you can write it like this. Now you can also go back, so you can go back from here to here, and you can write zeta to be a function of this position, that is zeta x and t. So basically this is the interchange between the Euler and the material coordinate. So when we say Eulerian derivative, that is just the usual derivative, that is del B by del T Eulerian derivative, and material derivative is usually defined like this. So that is at a fixed point x, and that is at the fixed material point zeta. Okay, so this is at fixed point, and this is fixed material point. So I hope you understand that in one case, in case of Eulerian, we are fixing the point. We are fixing the point at which we are there. So you are fixing this point. In another case, we are fixing the material point, and we are just following this. Can make it with a color. So basically, we have fixed this. Let's say we have fixed this. Then we are following this after this, and we are going here, here. So in one case we fixed our position, in another case we have fixed the particle. So basically we are going to relate these two. Okay, so to understand, to feel it, there is an example of skydiver problem that is there in Lille. So basically what happens is that there is a skydiver who is diving in the sky, and there is a temperature profile. So there is a linear temperature profile, that is T0 here and T1 here, and if you see, there is, if you fix the point, you will see no gradients. Okay, if you fix the point, you will see no gradient in temperature. So that is the Eulerian picture. But if it is coming with velocity v, then it is, with time it is changing. It is with time the temperature is not changing, but as the person is coming down, he feels the change in the temperature in the z direction, and it means that the Eulerian derivative is 0, but the Lagrangian derivative is non-zero, and that is because, and it means that dt, if I have to find dt by dt, it should not be 0, and that should be equals to minus u, that is the velocity of a person, that is just coming from the expression, and that is dt by dz. Okay, so to basically derive the correct relation between these two, so for now there is no change in temperature with time. Now if there is a change in temperature with time also, or any property with time, so let's see. So basically we understand that if we have to take the first case, if we have to relate this one, so dB by dt should be equals to the del by del t of b zeta t. So we have fixed the material point, and we are calculating the derivative of that is at the material point. Okay, now we know that zeta is nothing but So zeta is function of, okay. So basically we wanted to relate this with the Eulerian derivative, and in order to do so we know that zeta, so we want to convert from zeta to x. So basically when you are converting from zeta to x, you should write x should be a function of x, zeta and t. Okay, so basically if we are converting from uh, material to the Eulerian derivative, then we need to replace it like this. So what is the replacement? That is del b is now a function of, so zeta should be replaced by x, and that x is nothing but zeta t. Okay, so let's say we are having three coordinates x1, x2, x3. So x is x1, x2, x3, and so by applying chain rule we can get del b by del x1 and del x1 by del t plus del b by del x2, del x2 by del t plus del b by del x3, del x3 by del t plus, so this is at fixed zeta, right, at fixed material point. Okay, everything is at fixed material point, only we want to change, uh, we want to find what will be the b when we need to transform from material point to Eulerian point of reference. So at fixed, now this is at fixed material point, and then at fixed x this becomes del b by del t, so that is at fixed x. Okay, so basically what we get is v1 del b by del x1 plus v2 del b by del x2 plus v3 del b by del x3 plus del b by del t at fixed Eulerian point that we have found, and this should be equal to dB by dt. So or I can write it like dB by dt should be equals to v dot del b plus del b by del t. So we know this is nothing but substantial or material derivative or material derivative, and this is the Eulerian derivative, because now we are fixing it this x, so that is called as Eulerian derivative. So in the So that is all, that is the relation that I wanted to discuss to clarify it. In the next session, I will be going to discuss. So that's all done for this session. uh, I think in the next session I will be going to discuss more on Reynolds transport theorem. Then I will, so basically Reynolds transport theorem is nothing uh, but the transport of a property. Basically we will going to find the substantial derivative of a property, and we will see how it evolves. Then we'll derive the continuity equation and then Cauchy momentum equation, and then we'll go to the Navier-Stokes equation. If you have any doubt, you can ask me on that, and you can always mail me to this email ID. Okay. I hope everything you are able to understand. Still, if no, it is not, then you can always mail me. Okay. Thank you.